Hello, this is Dr. David Kreller of the Department of Chemistry, Georgia Southern University, and so in this video tutorial we'll be talking about some foundational concepts that underlie the chemistry of water. So we're going to talk about Bronsted-Lowry reactions. Then, with an understanding of Bronsted-Lowry reactions, we'll then go on to talk about the most important Bronsted-Lowry reaction that occurs in water that you could ever understand, called the auto-ionization of water. And so it's a process that reaches equilibrium. That all-important equilibrium has an important equilibrium constant. Now that will then lead us to an understanding of the pH scale. And in addition, we'll define pOH and see how that connects to pH and how you can convert between pH and pOH. Okay, so let's get started. So Bronsted-Lowry reactions are basically proton transfer reactions, or equivalently hydrogen ion transfer reactions. Let's use a specific example here of a proton transfer reaction occurring as two specific molecules interact. Here one is an NH3 or ammonium molecule and the other is a water molecule. As these two molecules interact, a hydrogen ion can be transferred from the water molecule to the ammonium molecule. Bronsted-Lowry reactions are proton transfer reactions. So this is proton transfer reaction. But now acids and bases are defined in terms of the roles that these molecules take. So you can see the water molecule, which is donating the hydrogen ion or losing the hydrogen ion, is referred to as an acid. So the molecule that gives off the hydrogen ion is called the Bronsted-Lowry acid, and conversely, the molecule that accepts the proton as it's transferred is called the base. The acceptor is called the base. Once the proton transfer reaction occurs, the products then are the ammonia molecule with the newly added hydrogen ion, so it's been turned into the NH4 plus, called the ammonium, the water molecule having lost the hydrogen ion, but retained the two electrons that were in the bond, has been turned into the form of the hydroxide ion. Chemical reaction written in equation form will be like this. Double arrows indicate that it does reach equilibrium. And so this is indicated that the NH3 is acted as the base, and the H2O is acted as the acid, but of course the base and acid having changed forms based on, I guess, the gain for the base and the loss for the acid of the hydrogen ion have changed forms, and these forms will be referred to as the conjugate acid and conjugate base respectively. Okay, now that we've defined or reviewed Bronsted-Lowry reactions, let's talk about the most important Bronsted-Lowry reaction that occurs within water. If you're only going to understand one chemical reaction occurring within water, this would be the one. Of course, you're going to learn about a bunch of chemical reactions in water, and the whole scope, the whole scheme is going to be interesting to you. But this is where you kind of start. In this reaction called the auto-ionization water, you'll see water molecules, some functioning one way as acids, and some water molecules functioning the other way as bases. And it's because of this interesting structure of the water molecule, where there's these bonds between oxygen and hydrogen, where that bond can be broken and the hydrogen given off, therefore being able to act as an acid. But the lone pairs on the oxygen atoms allow them to give hydrogen ions a place to stick when they act as bases. So in a Bronsted-Lowry auto-ionization reaction, one water molecule behaves like the base. The other water molecule puts the acid hat on, with the hydrogen ion being transferred from the acid water molecule to the base water molecule, and the products being hydronium ions and hydroxide ions. So now we know why within any sample of water, there's always some of these ions just automatically being produced by this auto-ionization reaction. This equilibrium is basically an example of a heterogeneous equilibrium where reactants and products can exist or exist in different phases. The reactants here are the water molecules in the liquid phase, pure liquid. And the products, the hydronium and hydroxide ions, are dissolved ions. So they're different phases. So when we write the equilibrium constant for this chemical reaction, which is called K, subscript W, we'll see that we only have on the top of this expression the concentrations of the products, hydrogen ion concentration, or hydronium ion concentration rather, multiplied by the hydroxide ion concentration. So in principle, you might say, well, where's the denominator for this? But it's heterogeneous equilibrium. As you can see, we have left out the pure liquid. So that's why the equilibrium constant expression looks kind of simplified. It's just simply the product of the concentration of the products. Okay, so from there, we can take the value of the equilibrium constant, which is 1 times 10 to the negative 14 at 25 degrees Celsius, which for the purposes of Chemistry 1146 course, Georgia Southern University, we'll always assume. So through this equilibrium, we'll see that the hydronium concentration, ion concentration, and the hydroxide ion concentration are totally interrelated. They do not take values just crazily independent of one another. They're totally intimately connected. If one changes, the other one changes. And so here's how they connect to one another. If you somehow specified the hydroxide ion concentration, then you would automatically know the hydronium ion concentration, or be able to calculate the hydronium ion concentration from that specified hydroxide ion concentration. And you can see an inverse relationship between the two. If the hydroxide ion concentration goes up, the hydronium concentration must go down. And this goes both ways. You could also say that if you have a specified concentration of hydronium ions, then you can calculate the hydroxide ion concentration from that. So if you know one ion concentration, you can calculate the other one. It's totally specified by this equilibrium relationship. Now let's define the parameter pH. So the concentration of hydronium ions, that concentration can vary over many orders of magnitude. It's something that makes water very interesting, and why a lot of chemical reactions are controlled by the concentration of these ions. Anyway, they can vary over many orders of magnitude. When you have a number that can vary over many orders of magnitude, it's quite often to talk about that number in terms of the logarithm of it. So that's what the pH does. It's a logarithmic index of concentration of hydroxide ions. So here's hydronium ions, Here's how pH is calculated, or here's what pH is. It's the negative log base 10 of the hydronium ion concentration. So basically, pH, it just gives us a way of talking about the hydronium ion concentration. That's what it's all about. pH is just all about hydronium ion concentration. But it's a logarithmic index. And it may seem a little weird because of the negative sign in there. If, say, hydronium ion concentration increased, well, the log of an increased number is also increased. But because of the negative sign out in front there, if the hydronium ion concentration increases and the log increases, well, because of the negative sign, then the whole thing decreases. A lower pH implies a higher hydrogen ion concentration. So it's kind of weird, and it kind of takes a little bit of getting used to, but you'll see the logic of it soon enough. So let's do a little bit of math together with this equilibrium relationship. And let's ask ourselves, what would be the concentrations of hydronium and hydroxide ions in a solution if those concentrations were equal? Now that we've learned that we can use the parameter pH to talk about the hydrogen ion or hydronium ion concentration, let's also then ask ourselves, okay, what's the pH of that? Mathematically, we don't know what they are. We're going to solve them as the variable x. Kw is 1 times 10 to the negative 14. That's the value of that equilibrium constant, is equal to product of the hydronium ion and hydroxide ion concentrations. So that's equal to x squared when we substitute in x times x. Basically, we're just finding x. So we have to take the square root of each side of this equation. So x is the square root of 1 times 10 to the negative 14. Well, that's 1 times 10 to the negative 7. But what's the pH? So pH is the negative log of that number that we just found. pH is negative log of 1 times 10 to the negative 7. The negative log base 10 of the concentration. So the log of 1 times 10 to the negative 7 is negative 7. And if you take the negative of that, it's just positive 7. In a solution in which the concentrations of hydronium and hydroxide ions are equal, those concentrations will each be 1 times 10 to the negative 7, and the pH will be 7. So that's your classical balanced or neutral solution. So now let's think about the fact that those concentrations are very rarely, or essentially never, the same. They're essentially always different, because there's different chemical species in the water that sometimes acid or basic properties and tilt those concentrations of these ions one way or the other. So to be able to describe all these different possibilities for solutions in terms of possible concentrations of hydronium ions and hydroxide ions, we have the pH scale. So we just talked about the idealized neutral solution, where those concentrations are equal, 10 to the negative 7, and the pH would be 7. Here's those concentrations are equal, but in reality, we know that those concentrations are very, very rarely the same. So solutions in which the concentration of hydronium ions is greater than hydroxide ions and the pH is less than 7, so on this side, those solutions are called acidic solutions. And conversely, solutions in which the hydroxide ion concentration is greater than the hydronium ion concentrations and the pH is greater than 7, i.e. this side of the pH scale, those solutions are called basic. So we'll just say that much about the pH scale for now, okay? And so we'll define pOH. Now that's not too hard to understand, really. If you know how to calculate pH, or P anything for that matter, you just take the negative log base 10 of that parameter. So pOH is negative log base 10 of the hydroxide ion concentration. And now how does it connect to pH? Well, to answer that, let's look at the equilibrium constant expression. It's an equation, of course, with this equal sign being very, very important, and so we want to manipulate this equation a little bit, and of course, it's totally okay to manipulate it, but, however, if we do anything to one side of the equation, we have to do the exact same thing to the other side of the equation to maintain the equality. So let's just take the negative log of each side of the equation. Alright, so the negative log of Kw is equal to the negative log of this product, hydronium ion concentration times hydroxide. But we're going to use a law of logarithms. The log of something that's a product, say the log of A times B, is equal to the log of A plus the log of B. So when we apply this law, we see that this splits up and becomes the negative log of hydronium concentration plus the negative log of the hydroxide ion concentration. But these have been defined. Well, that's pH and pOH. And what's the negative log of Kw? Well, what's the negative log of 1 times 10 to the negative 14? Well, that's 14 is equal to pH plus pOH. And so therefore, you see how the two are connected. You see that they always have to add up to 14. If they are equal, they're both equal to 7. 7 plus 7 is equal to 14. But of course, if one goes up, the other one goes down from there. And if you had a specific value of pH in mind, and you had the solution had a specific pH, and the pOH would then be defined, but could be calculated as 14 subtract the pH. And similarly, if there was a specified value of pOH, the pH would then therefore be set, and then just could be calculated as 14 to subtract the pOH. So now we know that there is some weird thing about water, that within the water there's always these two kinds of ions, hydronium ions and hydroxide ions. And it's really important in terms of the condition of the water, exactly what those concentrations are. So that's something that scientists need to talk about, those interconnected concentrations of things. So now we've talked about 4 ways of talking about the condition of water. We've of course got hydronium ion concentration and hydroxide ion concentration. And we've got pH and pOH. And really, they're just different ways of talking about the exact same thing. And although there's 4 different ways of talking about the condition of the water, they're all kind of redundant on each other. And really, if you know one, the other 3 are then specified. And so you can interconvert from one to any of the others. So let's review what we've learned so far. If you know the hydrogen ion concentration or the hydronium ion concentration, you can calculate the hydroxide ion concentration. There's the formula you would use. Okay. And conversely, if you know the hydroxide ion concentration, you can calculate the hydronium ion concentration just by that equation. So if you know the hydronium ion concentration, then this pH is specified. You just take the negative log of that number. And conversely, if you know the pH, then you know the hydronium ion concentration, that calculated of 10 raised to the power negative pH. That's how you convert between those two. Okay, if you know hydroxide, then you can calculate pOH by that equation. And if you knew pH, then you can calculate hydroxide ion concentration. If you know pOH, you can calculate pH, of course. They have to add up to 14, so the pH is just 14 minus the pOH. And similarly, if you knew the pH, but you wanted to calculate the pOH, then of course that's just 14 minus the pH. So that's everything we've talked about in this video. Okay, and that brings us to the end of this part 1 video. And so in the second video that follows, we're going to talk about the theory of weak acids and weak bases.